All right, this is Mr. McCord's ICP class. We're going to continue on with Unit 5, assignment number 1, looking at ionic bonding and making ionic compounds. But we're going to do a couple tougher examples this time. We're looking at making an ionic bond, an attraction between zinc and sulfur. We've also got this odd sort of Roman numeral 2 there, which we'll kind of talk about. Okay, so first off, I want to see how many valence electrons zinc is going to gain or lose as an ion. Okay, now if I go look at where zinc is on the periodic table, it's in the transition metals. It's in that middle section that we don't really talk about with a number of valence electrons or a charge. There's no shortcut. There's nothing. So how do we figure out how many valence electrons something's going to lose or gain if it's in that middle section? Well, that's what that Roman numeral 2 is for. Okay? Whenever you see a Roman numeral next to an element from the transition metals like zinc or iron or titanium, vanadium, chromium, that's basically telling you how many valence electrons that metal is going to lose. How many valence electrons lost? How many valence electrons we're going to give up? Now, coincidentally, however many valence electrons you lose is how positive your ion becomes. So in this case, if zinc has a Roman numeral 2, that means it's going to lose 2 valence electrons, which means it's going to have a positive 2 charge. Okay. If you are not kind of up to date on your Roman numerals, here's what they are. I is 1, II is 2, III is 3, IV is 4, just V is 5, and then VI is 6, and we typically don't go higher than that in chemistry. You can always look them up, or I'll usually have them on a reference sheet for you. Okay, so in this case, zinc is going to lose 2 valence electrons to get that positive charge of 2. And again, we know that not because of the periodic table, but because of that Roman numeral there. Right there, the Roman numeral 2. Okay. Sulfur, though, is in the regular side of the periodic table that we can just look up. So we go find sulfur. It's in group 16. It's in the oxygen group, which means it should gain 2 valence electrons to reach 8 valence electrons. And if it gains 2 negatively charged electrons, it's going to become that negative. So it should have a charge of -2. Okay. So other than that weird Roman numeral thing we had going, basically the same stuff. So let's draw it out. So our zinc has 2 valence electrons. Sulfur starts with 6 valence electrons. Okay, so we want to make this work out for everyone. We want our zinc to give up both of those electrons, and we want sulfur to take 2 electrons. Well, this is kind of like with sodium and chlorine. It's a match made, perfectly, where zinc can give up its 2 electrons to the sulfur. This needs to lose 2, this needs to gain 2. Okay? So we can trade more than 1 electron to the same element. Not only can we kind of split where those electrons go, we can also send multiple at a time. And that's exactly what's going to happen here. Zinc is going to give up both of its electrons to this sulfur. So that way we wind up with zinc with 0 valence electrons. So no dots. And we show its charge of +2 up in the corner here. And sulfur with all 8 of its valence electrons. 1, 2, 3, 4, 5. It's 6 plus the 2 it just got from the zinc. Okay. Which helps it become that ion with a -2 charge. So we put that in the top right. So this is our ionic compound made of zinc and sulfur. Just to double check it, zinc has 0 valence electrons, which is good. Check that off. Sulfur has 8 valence electrons, which is also good. Check it off. And last thing, we want the charges of those ions to cancel out to 0. Well, +2 -2 cancel out to become 0, so that is a happy ionic compound. Okay, in this example, we're going to try and make an ionic bond between some ions of silver and nitrogen. Now, silver is another metal that is in the transition metals section in the kind of middle of the periodic table. So there isn't a shortcut to figure out how many valence electrons it's going to lose that we can find on there. But when we make a compound, when we make silver bond with something, we'll stick a Roman numeral on it that will tell us how many valence electrons it is going to lose in this case, and it'll also tell us how positive that charge should be, since each electron that we lose is going to give us more and more positive charge. So in this case, the Roman numeral after our silver here is Roman numeral 1. So this is going to lose 1 valence electron, which means it's going to have a charge of +1. Okay, not too bad. Our nitrogen that we're trying to bond with is something we can find on the periodic table. It starts with 5 valence electrons, as it's in column 15. All right, it's in the nitrogen group, heads up the top there. So it should have to gain 3 valence electrons to get to 8 valence electrons to get that full set. So gaining 3 electrons will give this nitrogen a -3 charge, since it's going to become negative for every electron that it picks up. Okay, so to make our silver and our nitrogen happy, each atom of silver we deal with needs to lose 1 valence electron, and each nitrogen needs to gain 3 valence electrons. So just 1 atom of each is not going to be enough to make this happy. We're going to have to get crafty. So each silver atom wants to give up 1 valence electron. So I'm just going to draw it with 1 valence electron, 1 dot, that it's going to give away to something that wants it, like this nitrogen atom. So, giving up that 1 valence electron has made this silver atom happy. It becomes an ion. That's great. But this nitrogen still isn't there yet. Gaining 1 valence electron gets it from 5 valence electrons to 6 valence electrons. Better, but not where we need to be. So, we need another thing to give another valence electron. We need another atom of silver. Okay. Again, starting with 1 valence electron that it's going to give up to this nitrogen. Okay, that would make that atom of silver happy, and our nitrogen is getting closer, so it's now going from 5 valence electrons to 6 to 7. It still needs 1 more, so we need 1 more silver atom. Some of these compounds take a while to work out because it's hard to get everything happy, especially if you've got weird charges and stuff, and you've got a lot of valence electrons to give and take. Okay, so if things just aren't working out after 1 or 2 steps, keep at it. You will find a point where you can get everything happy, like in this case. where it takes 3 silver atoms to give up their valence electrons to just one of these nitrogen atoms to make everything happy here. Now we just have to show how the charges get everything to stick and attract to each other and bond to make an ionic compound. Okay, so now each of my silver atoms has 0 valence electrons, which is good. My nitrogen atom has 8 valence electrons, which is also good, so they're happy in that sense. Now, we have them in brackets here to show they're going to have charges, and we put the charge in the top right of that little set of brackets. So each silver ion should have a charge of +1, just like we said before. +1, +1, +1, like that. And our nitrogen should have a charge of -3 from picking up those 3 valence electrons. Okay, and that is our ionic compound. Now again, a happy ionic compound altogether should have a neutral charge. So let's check. We've got a +1, a +1, a +1. So that's a total of +3 charge. And then a -3 charge here. So +3 minus 3 gives us 0. That's a neutral charge. That's what we want. Okay? Everything's going to keep attracting to each other until we get all those charges to cancel. So these 4 ions all together will make this ionic compound between silver and nitrogen. Okay, so a couple things to note before we move on. So in our compound here, we have our charges written up as like +1s and -3s. If you go look up stuff online, if you see videos, things on Google, look at a textbook, you'll notice that a lot of times these are switched around. So you'll see like 1+ or 3- or 2- or 2+ instead of putting the positive and the negative first. That's just kind of a traditional chemistry thing we do with charges. I personally don't have a problem putting them one way or another for this class, but if you are going to move on to advanced chemistry, you'll see it kind of flip the other way. I usually like writing it out like this just because it's straight to the point and it's clear. You've got a +1 charge or a -3 charge, but just in case you see like something flipped or turned the other way, or if I write it that way on instinct, it's not wrong. In fact, the other way is probably a little bit more accurate, but it's going to mean essentially the same thing for us. Okay? Now, you may also see sometimes that instead of writing out a +1 or a -1, we show just the sign of that charge. So instead of writing a +1, I could just write a plus. Like that. Okay? After all, if I'm writing a plus, that kind of implies it's at least a +1 charge. Okay? Now, if it was a +2, I would need to write the 2. If it was a +3, I would need to write the 3 because I want to show how positive or negative it ends up being. But if it's just a +1 or a -1, we can kind of leave out the 1. It's implied. So you may also see it looking like this. Okay, let's do one more example where we are putting together zinc, Roman numeral 2, and nitrogen. Okay, so both of these are something we've seen before. We're just going to kind of put them together in a new way. Okay, so my zinc, Roman numeral 2, that Roman numeral 2 just means that I'm going to be losing 2 electrons. Okay, which means we're going to wind up with a charge of +2 for losing those 2 negatively charged electrons. All right, just like we saw before, nitrogen starts with 5 valence electrons, so it's going to gain 3 electrons, which means it winds up with a -3 charge. So anytime I have an ion of zinc, Roman numeral 2, or nitrogen, like this, they're going to be like this. I should have zinc losing its electrons to reach a +2, or nitrogen gaining 3 electrons to get a -3 charge. Okay? But, just like we saw before in the previous examples, sometimes it's not so easy to get everything to work out. So this is going to be kind of a tough one. We'll see if we can figure it out. Okay, so we're going to show each of our zincs with 2 valence electrons. give it 2 dots there. Okay. My nitrogen is going to have 5 dots for 5 valence electrons. Okay, that's fine. So if I'm trying to get rid of these and trying to get electrons for this guy, I should give my electrons over to the nitrogen. That's all well and good. My zinc is going to be happy now. It's gotten rid of its 2 electrons, but nitrogen is still only at 7, so it's not quite there yet. So what I need is another zinc atom. And it also is going to start with 2 valence electrons. Okay, so I can give one over to this guy. All right, which means my nitrogen has now gone from 5 valence electrons to 6, 7, 8. So now the nitrogen is happy. But my zinc isn't. It still has 1 more valence electron to give up, so we're not done yet. I need something else to take that valence electron, like another nitrogen atom. This is going to get a little messy. Okay, so I've got my nitrogen over here with 5 valence electrons. That's something I can give this electron away to, so my zinc can shell out that one. So now this zinc is happy, which is good, but this nitrogen still isn't happy. So it's gone now from 5 valence electrons to 6 valence electrons. Last thing, I need one final zinc atom that's got 2 valence electrons to get this guy from 6 to 8 valence electrons. All right, there's my last zinc with 2 valence electrons. That get this nitrogen atom to 8 valence electrons. Okay, so this is our give and take to make this compound between zinc and nitrogen. All right, took a while, but we can always get there. All right, we just have to kind of keep working at it. All right, so when I write this over here, I'm going to clean this up a little bit. It doesn't really matter where you put the ions next to each other in a structure like this, the drawing that we do, but I like to try and get them kind of meshed in so it looks like the charges are kind of clustering up together in the right way. Okay, so I've got my zinc ions all without any valence electrons. They've now reached a charge of +2, so I'm going to write that up in the corner. And my nitrogen atoms have reached 8 valence electrons. They now have a charge of -3 each. To make a happy ionic compound, I want to make sure all of that charge ends up canceling out. So I've got +2, +2, +2. Well, that's +6. Then I've got -3, -3. That's -6. So +6, -6 come together and cancel to make a charge of 0. That's neutral. That's a good ionic compound right there. Now, one last thing. So we write a Roman numeral after a transition metal like this to show how many valence electrons it's going to lose, how positive it's going to get, but that doesn't mean it's always going to act like that. So you might come to a problem later that has zinc or silver or iron or something like that that has a different Roman numeral than one you've seen in an example. Okay, that's fine. Depending on the situation, we can have the same element give out a different number of valence electrons depending on what it bonds with and how it bonds with it. Okay? Sometimes even between the same 2 elements, we'll get a different way that they give electrons to each other. Okay? So if you are looking at an element like iron, and sometimes it's got a Roman numeral 1 or a Roman numeral 2 or a Roman numeral 3, that's fine. Okay? Just work with whatever it gives you in that specific problem. That's what makes transition metals kind of tricky, and it's why we haven't really dealt with ions of them until now. depending on the situation we put them in. They might bond differently. They might shell out valence electrons differently. Okay, so just pay attention to the Roman numeral for that specific problem and look at how many valence electrons it's going to give, how positive it's going to become, to see what kind of compound it's going to make in that case.